Not only do sine, cosine and tangent relate to the unit circle, but they also relate to the ratios between the length of the sides and the angles of a right-angled triangle. These ratios, known as the trigonometric ratios, are the focus of this video. The trigonometric ratios are incredibly useful to us in computer graphics and programming. By relating the lengths of the sides and the angles of a right-angled triangle, they allow us to calculate missing information, if you will. If we know certain lengths and certain angles, we can find out other lengths or other angles. And this is extremely helpful when problem solving. If we're solving some problem and using triangles to solve that problem and try and find certain pieces of information, perhaps the angle between two edges of a right-angled triangle or the length of the side of that triangle, we can apply these trigonometric ratios in order to find that information. Now, whilst the trigonometric ratios themselves apply only to right-angled triangles, by subdividing arbitrary triangles into multiple right-angled triangles, trigonometry can actually be applied to those triangles to solve problems that relate to any triangle, not just right-angled triangles. And we'll see how to do that in later videos. So starting out in this video, allow me to draw a right-angled triangle here on the whiteboard. So let's draw in our hypotenuse and then two edges that are perpendicular to each other, which means, of course, they meet here at a right angle. Fantastic. And then I'm going to bring up a layer that I can draw on. Excellent. So looking at any two sides of a right-angled triangle, for example, let's pick on these two sides here. Looking at any two sides, we know that the ratio between these two sides directly results in the two angles that are here. We could look at either of these two angles. I'm going to pick on this guy, and we know that this angle directly defines the ratio between these two edges, or in other words, these two edges directly define this angle. And how do we know that? Well, the only way to get that angle is to have these two edges of these exact lengths, or a uniform scale of those lengths. If either of these edges changes size and the other edge doesn't change size proportionally to it, the angle must change. And we can clearly see this. If I was to shrink down, say, this edge here so that it became shorter than it was previously, but I wasn't to change the other edge proportional to that, the only way that our hypotenuse could come up and meet with this edge is if this angle and this angle both change. We can see that the angles must change. Therefore, the only way to get this particular angle, and of course this particular angle up here, is if the ratio between these two edges are the same. So for any angle that isn't the right angle, so for this guy or this guy, but not our right angle, because he's always 90 degrees, he never changes. But for any one angle that isn't a right angle in a right angle triangle, there are relationships between that angle and any pair of edges. And this logically makes sense because given any two edges in our triangle, the third is automatically defined. If we have two edges, we automatically have the third because it runs between the endpoints of the other two edges. And there's a naming convention used to refer to the edges of a right-angled triangle when we're relating them to a particular angle. Now, the hypotenuse is always called the hypotenuse. I'm going to label this with a capital H, but over here I'm going to say hypotenuse. And the hypotenuse, as we saw in volume 1, is the edge of a right-angled triangle that sits opposite the right angle. And that's always named the hypotenuse. It doesn't matter if we're talking about this angle, or if we're talking about this angle up here. This guy, the hypotenuse, is always, always, always called the hypotenuse. Now, the other two edges, they are named based on their relationship to the angle that is in question. So if we were talking about this angle right here, then the two other edges are named as follows. The edge that sits opposite the angle in question is rather logically referred to as the opposite edge, or often it's just called opposite. So I'm going to label this guy with a capital O, and over here I'm going to write opposite. So the edge that sits opposite our angle is the opposite edge. The other edge that forms our angle with our hypotenuse here, or I prefer to think of it as the edge that touches the angle, if you will. It comes in and touches the angle. This edge is called the adjacent edge. It's adjacent or next to the angle. So I'm going to write capital A. I'm going to label this adjacent. So we have our hypotenuse. It's always called hypotenuse, and the other two edges are called the opposite and the adjacent. And of course, the opposite is the edge that is opposite the angle in question. The adjacent is the edge that is touching the angle in question. And of course, it's all relative to that angle. So if we were to look at the other angle, so I'm going to scroll down just a bit. I'm going to draw another right angled triangle, hopefully quite close in shape to our first. So there we go, with another right angled triangle. Back to my layer I can draw on. The hypotenuse is always called the hypotenuse, but if I was talking about our other angle, notice this edge on the bottom is now opposite our angle, and this edge here at the side is touching our angle, and that means that's the adjacent edge. So when we're looking at the other angle, the naming convention of these two edges changes, so that's always relative to the angle in question. So given this naming convention of hypotenuse, opposite, and adjacent, there are three possible ratios between these edges. Now again, remember that these names are relative to a particular angle in question. So if I was to scroll down just a bit and give myself some room on the whiteboard, there are three different ratios between all of these edges, or if you will, three different pairings of these edges. The first is our opposite and our hypotenuse. So we could say there's a ratio of our opposite edge divided by our hypotenuse. So that's one of our possible ratios. We could also take our adjacent edge and our hypotenuse and pair those. So another ratio is adjacent divided by hypotenuse. And our third pairing of edges would be the opposite edge and the adjacent. So we could take our opposite and divide that by our adjacent. So we have our opposite and our hypotenuse, our adjacent and our hypotenuse, and our opposite and our adjacent. These three different pairings, these three different ratios, are the only pairings of these edges that we can have. Now, due to the way that sine, cosine, and tangent are defined on the unit circle, we actually find that these three ratios of edge pairings are actually equal to sine theta, cos theta, and tan theta, where theta is the angle in question. So if we were looking at this particular angle, and we called that angle theta, then knowing that this is our opposite edge, this is our adjacent edge, and this is our hypotenuse, these three ratios relate to the sine, cosine, and tangent of that particular angle. So our trigonometric ratios can be written, as I scroll down, because I want as much room as possible for these, as the sine of theta, our angle in question, is equal to the opposite edge to that angle divided by the hypotenuse. The cosine of our angle in question is equal to the adjacent edge. So the edge that touches that angle divided by the hypotenuse. And the tangent of that angle is equal to the opposite edge divided by the adjacent edge to that angle in question, theta. So these are our trigonometric ratios, and they're so incredibly useful that it really is worth remembering them. So to assist in remembering them, there are a couple of devices that are often taught. The first is to simply take the first letter of each word, giving us S from sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. Tan is equal to opposite over adjacent. So taking the first letter of each of these, and that can then be rewritten into sounds, if you will. So we have the function the top of our division, the numerator, and then the bottom of our division, the denominator, in that order, giving us the sound so, ka, and toa. So so, ka, toa. And what a lot of people do is they form those three sounds into the word SOHCAHTOA. And they simply remember SOHCAHTOA. They remember that that breaks down into three parts, so, ka, and toa. They remember how each of these parts are spelled, S-O-H, C-A-H, T-O-A, and from there they break that down into sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, tangent is equal to opposite over adjacent. So that's how a lot of people remember it. But personally, whilst this can work, I think that, if you forget how to spell either so, ka, or toa, or even if you forget SOHCAHTOA, because it's not a normal word, it's not something that we're used to using in everyday language, it's quite an abstract concept. If you forget any of those, then you're going to not be able to remember these ratios. And because the ratios are so important, I like to remember something that makes it really easy to remember them. So the way I learned to remember these ratios, and I will never forget the day of school where I got taught this, the reason why will become very apparent later, I was just a young teenager at the time, is using the following mnemonic device. And just a warning, this device is very tame, but it may offend some of you. So I just wanted to throw that warning out there. My intention obviously is not to offend anyone, it's just to help you learn and remember this stuff. And I feel that this is so important that if I can offer a device that really does help everyone to remember it, then I think that's worth throwing out there, even if there's a very small 1% chance that it may offend someone. So again, we're going to take the first letter of each word, and again, we're going to use those to form this abstract word SOHCAHTOA, but we're not going to stop there. We're then going to assign an English word to each of these letters, giving us a little phrase that we can remember, which will tell us how to spell SOHCAHTOA. So starting out, we have sex on hard concrete always hurts those outer areas. Again, that's sex on hard concrete always hurts those outer areas. So yes, it's very silly, but throughout all the years since I first learnt this device, I have never, ever forgotten it. Now the same cannot be said about quite a lot of other things that I've been taught. So I really hope that this works as well for you as it has done and continues to do so for me. So we've got our three trigonometric functions of sine, cosine and tangent, and we know how these relate to the ratios of the edges in our right-angled triangle, which gives us our three trigonometric ratios. But how do we use them? Well, there are two different ways that we can use these trigonometric ratios. The first is to find the length of a missing edge, and that's what we're going to focus on in the rest of this video. The second is to use them to find a missing angle, and that's going to be the focus of the next video. So to find the length of a missing edge, all you're going to need is the length of one of the other edges and the value of one of the angles in our triangle. Knowing these two pieces of information, we can then find the trigonometric ratio that relates the information that we do know to the edge that we're trying to find. For example, let's consider the following right-angled triangle. So let's say I had a triangle that looks like this. And it is a right-angled triangle, because we know the trigonometric ratios only apply to right-angled triangles. And let's say we knew that there was an angle in this triangle, which I'm going to call theta, that was 35 degrees. And let's say we knew the hypotenuse was 10 units long. And let's say we're trying to find the length of this vertical edge. So we're trying to find how long is that edge. Well, the first thing we need to do is to decide on the naming convention for our edges. We already know that this edge right here is our hypotenuse, since it is opposite the right angle. We can see that this edge, because it's opposite the angle in question, our theta, in this case, this edge is our opposite edge. And this edge, because it is touching our angle theta, it is the adjacent edge. And now that we've named our edges, we can see we're trying to find our adjacent edge, and we know our hypotenuse and we know the angle theta. So what we need to do is we need to look for a trigonometric ratio that somehow relates the hypotenuse, the adjacent, and the angle theta. So again, that's the hypotenuse, the adjacent, and the angle theta. And we can see hypotenuse, adjacent, angle theta. Our cosine trigonometric ratio gives us exactly that. So we know our hypotenuse, that's a known, so that's a constant value, if you will, in this equation. And we can calculate the cosine of our angle, whether that's using a scientific calculator or whether that's using the trigonometric functions in a programming language. We can find the value for cos of, in this case, 35 degrees. It will give us some value between -1 and 1. So this is a known constant value, which means in this equation, the only unknown value is our adjacent, the edge that we're trying to find. And that means we can rearrange our ratio, our cos theta equals adjacent over hypotenuse. So cos theta, I will abbreviate this, equals to adjacent over hypotenuse. We can rearrange this to find our adjacent edge. So how will we rearrange this equation to get adjacent on its own? Quite simply, we'll multiply both sides by the hypotenuse. So cos theta multiplied by the hypotenuse is equal to our adjacent edge. We can now take this and we can plug our information into it. So that means we can take the cos of 35 degrees and multiply that by 10, and that's going to give us our adjacent. Now I'm going to use the scientific calculator that comes with Windows as standard to calculate this. So rather than just calculating this value off camera ahead of time, I actually want to show you how we can use the trigonometric functions of this calculator. And that's because no matter which scientific calculator you're using, whether it's a physical one or a calculator that's just software on the computer, whether with Windows or another operating system, or there are calculators out there available for free on the internet, they all work in similar ways. They provide similar functionality and usually work in the similar way. It's quite an intuitive way. So I wanted to show you so that if you haven't ever worked with a scientific calculator or haven't ever worked with the trigonometric functions of a scientific calculator, you now get some hands-on experience seeing how to work with a calculator to find these values. So I'm going to open up our calculator, and the first thing you'll notice is this calculator is just in standard mode. We have our simple operations, numerical pad to enter numbers, but we don't have access to our scientific functions. So if I come up to view and then view scientific, our calculator opens out and we get access to a huge amount of functionality. The functionality that's important to us is going to be our 3 trigonometric functions of sine, cosine, and tangent. Now, you'll also notice up here that we are set to degrees. Most, if not all, scientific calculators will let you specify what unit of measurement we're using to measure our angles. We're dealing with degrees here. That means any numbers I'm entering into our cosine or sine or tangent trigonometric functions will be in degrees. Thus, to get the correct answers, the calculator must be set to work in degrees. We could set it to radians, but then we wouldn't be able to enter 35 into our cosine function. We'd have to enter the equivalent of 35 degrees in radians into that function. But of course, we're just going to work in degrees, keep everything matched to our whiteboard, keep everything nice and simple. So I need to calculate, to begin with, I need to calculate the cosine of 35 degrees. Once I have that value, I then need to multiply that by 10. So how do I calculate the cosine of 35 degrees? Well, the way this calculator works is if I enter a value and have that value displayed up here on the main line of the calculator, if you will, and then press a trigonometric function, it calculates the trigonometric function of that value. So for example, if I enter 35 for 35 degrees and then press cosine, it calculates the cosine of 35, and that's about 0.819. So that's the cosine of 35 degrees, 0.819. I can multiply that by 10 by our hypotenuse, and that is equal to about 8.19. So our cosine of 35 degrees multiplied by 10 is equal to our adjacent, which is about 8.19. 8.19. So our adjacent edge is about 8.19 units long. And that's all there is to it. So let's try another couple of examples to get used to this. So we've got our same triangle, but in this case I want to find the length of our opposite edge. Now we have two choices here. We could relate the opposite to the adjacent, which we just found, or the opposite to the hypotenuse. I'm going to use the hypotenuse because we know that the length of the hypotenuse is exactly 10 units, whereas the value we just calculated for the adjacent is only approximate. So we need to find a trigonometric ratio which relates the hypotenuse and the opposite edge of a triangle to the angle theta. If we scroll back up, we're looking for the hypotenuse and the opposite. Hypotenuse, opposite. We are using our sine trigonometric ratio. Now again, we can calculate the value of sine theta. We know the hypotenuse, and that means we can rearrange this to find our opposite. So scrolling down, I know that the sine of theta is equal to the opposite over the hypotenuse. How do we rearrange to find our opposite? We multiply both sides by the hypotenuse. That gives us the sine of theta multiplied by hypotenuse is equal to our opposite. We can plug numbers into this. That means the sine of 35 degrees multiplied by our hypotenuse, a length of 10, is equal to our opposite edge. We can now use our calculator once again, as I grab the calculator, there we go, once again, to calculate this. So we need to calculate the sine of 35 degrees. So 35, we are in degrees, sine, and that's about 0.574. We can multiply that by 10, the length of our hypotenuse, and that's equal to 5.74 thereabouts. So the sine of 35 degrees times 10 equal to our opposite edge is equal to about 5.74. So 5.74. Fantastic. So it really is that simple. So before I set you guys some questions, let's walk through just one more example on the whiteboard. So I'm going to draw another triangle this time. It's going to look similar to this guy, but he is in fact a different triangle. So I'm going to draw another triangle. So here is our triangle, and it's a right-angled triangle. Very important, of course, our trigonometric functions only relate to the right-angled triangle, or rather our trigonometric ratios only relate to the right-angled triangle. Let's say we know this angle, we're going to call this angle theta, and we know that it is 75 degrees, and let's say we know the length of the vertical edge is 15 units, and I want to find the length of the horizontal edge. So what are the steps we need to take? Well, the first thing, remember, is we need to find the naming convention of these edges. We know our hypotenuse, it's opposite the right angle. This edge is our opposite, it's opposite the angle that we know, the angle in question. So because we're going to be working with this angle in our trigonometric ratios, we have decided that we're working with this angle. This edge becomes the opposite edge. And that means, of course, this edge here that's touching our angle is the adjacent edge. So we are trying to find the adjacent edge, and we know the opposite edge. So that means we need to look for a trigonometric ratio that relates the adjacent and the opposite. Scrolling back up, adjacent and opposite, well, that is our tangent trigonometric ratio. So let's scroll back down. We can see that the tan of theta is equal to the opposite over adjacent. Tan of theta is equal to opposite over adjacent. We are trying to find our adjacent edge. So let's rearrange this to find the adjacent edge on its own. So I'm going to multiply both sides by the adjacent. So a times tan theta is equal to our opposite. Then divide both sides by tan of theta, which gives us that our adjacent is equal to the opposite divided by the tan of theta. If we put our numbers in, that means our adjacent is equal to 15 over the tan of 75 degrees. And we can use a scientific calculator to work the value of this out. So let's start out, we need to take 15 and divide that by the tan of 75. So of course I enter 75 in degrees, click the tangent button to work out the tan of 75, and then if I press equals, it's going to tell me that 15 divided by the tan of 75 is approximately equal to 4.02. So this is approximately equal to 4.02, which means our adjacent is 4.02 units long. And again, that's all there is to it. Alright, so let's put all of this new knowledge that we've gained over this and the previous two videos to the test. So I'm going to start out by bringing up a new whiteboard. So new whiteboard, and let's hide all of this. Fantastic. And then I'm going to scroll on up. And let's start out by drawing a right angle triangle. So something like so. This is a right angle triangle. Fantastic. And give myself a layer to draw on. So I probably should know that this is indeed question 1. And in this question, we know that this angle right here is 40 degrees. And the length of this edge is 17. And I would like you to tell me the length of the edge I've just labelled with a question mark. So go ahead and pause the video. Give this an attempt. If you come up with a solution or you get stuck, unpause the video and I am going to work through the answer here on the whiteboard. Okay, welcome back everyone. So we know that our angle is 40 degrees and we know the length of our hypotenuse is 17. And we're trying to find the length of this edge here. It touches our angle. That means that we're trying to find the length of our adjacent edge. So we need a ratio that relates our hypotenuse and adjacent edges. And we've seen that that ratio is our cosine ratio. So cos of theta is equal to the adjacent over the hypotenuse. And that means our adjacent is equal to the cos of theta multiplied by our hypotenuse, simply rearranging this equation here. With that, we can plug our numbers in, so it's equal to the cos of 40 degrees multiplied by 17. We can now use a scientific calculator to work that value out. So the cosine of 40 degrees, I'll enter 40, then click cosine, I am in degrees, that's about 0.766. I can multiply that by 17 equals, so the length of our adjacent edge is about 13.023 units long. So it's approximately equal to 13.023 units. And it's that easy. If you made any mistakes, make sure that you labeled your edges correctly. So this is the hypotenuse that we knew because it's opposite the right angle. And this is the adjacent edge because it's touching our angle. So make sure you labeled those edges correctly. Then make sure you selected the correct trigonometric ratio. We're dealing with the adjacent and the hypotenuse. That means the only ratio that relates those two edges is our cosine ratio. If you picked the correct ratio, make sure you rearranged it correctly to find the adjacent edge. We multiply both sides by the hypotenuse, and that gives us the adjacent is equal to the cosine times hypotenuse. And finally, if you got that far but still made a mistake, check how you're using your scientific calculator and make sure that you're getting the same answer. We want to find the cosine of 40 degrees and multiply that result by 17. So if your calculator works slightly differently, look in the instructions to see how you find the cosine of an angle, and then once you've found that, multiply that by 17. And if you get all of those stages correct, then you'll get the answer 13.023. So that's question 1. Let's move on to question 2. I'm going to draw another triangle. It's going to look pretty similar, but it is a different triangle. So here's another triangle. Let's make a right angle. Fantastic. And jump back to the whiteboard that I can draw on. Fantastic. So we know an angle in this triangle is 20 degrees. I know this edge right here, this vertical edge, is 5 units long, and I'd like you to tell me the length of the edge I have just marked with a question mark. So go ahead and pause the video, give this a go. When we come back, I will work through the solution on the whiteboard. Okay, welcome back everyone. So we know our angle's 20 degrees. This edge that we know here is opposite our angle, so this is the opposite edge. And the edge that we're trying to find is opposite the right angle, and that means it's the hypotenuse. So I'm looking for a trigonometric ratio that relates our angle to the opposite edge and the hypotenuse. There's only one ratio that does that, and that's the sine ratio. So sine of theta is equal to the opposite over the hypotenuse. We need to rearrange this to find our hypotenuse. I'm going to multiply both sides by the hypotenuse. So hypotenuse times sine of theta is equal to the opposite, and then divide both sides by sine theta. That's going to give me the hypotenuse is equal to the opposite over sine of theta. We can then plug our values in. Our opposite's equal to 5, and we're finding the sine of 20 degrees. We can now use our scientific calculator to find the answer of this. So let me clear my answer from before. So I'm going to take 5, and I want to divide that by the sine of 20 degrees, and that gives me the hypotenuse is approximately 14.619 units long. So the hypotenuse is approximately 14.619 units long. So nice and easy, nothing to it. We now have one last question that I'd like to set in this video. So I'm going to scroll down just a bit further. This is going to be question 3. Again, this is the final question in this video. And let's draw ourselves another right-angled triangle, so something like such. The right angle is this guy up here. And then I'm going to jump back over so I can draw on a whiteboard. So I'm going to say we know this angle to be 60 degrees, and I know this edge is 12 units long. And I'd like you guys to find the length of the edge I have just marked with a question mark. So go ahead and pause this video, and when we come back I will work through the answer on the whiteboard. Alright, welcome back everyone. So we know our angle is 60 degrees, and we know that this edge right here is the hypotenuse because it's opposite our right angle. But we're not interested in the hypotenuse, it has nothing to do with this problem, but I wanted to point out that he's the hypotenuse so that we know that these two edges are the opposite and the adjacent. Which is which? Well, we're dealing with this angle right here. So the edge opposite this angle is the opposite edge. That's the guy we're trying to find. And the edge that's touching this angle is the adjacent edge. That's the guy that we know. So we need a trigonometric ratio that relates the adjacent and the opposite. There's only one of those. That's the tangent ratio. So tan of theta is equal to the opposite over the adjacent. We can rearrange this to find the opposite simply by multiplying both sides by the adjacent. So tan of theta times adjacent is equal to the opposite. We can plug our numbers in. So tan of 60 degrees multiplied by 12 is equal to the opposite. And we can then use a calculator to work out this value. So let me clear my previous result. So I want the tan of 60 degrees. So 60, pick the tan button. That gives me the tan of 60 degrees. I'm going to multiply that by 12. And that tells me the length of that opposite edge. The edge we were trying to find is approximately 20.785 units long. So the opposite edge is approximately 20.785 units long. So if you've worked your way through all three of those questions and you got everything correct, really well done. Once you get the hang of it, it's so simple, but I can understand that when you're still getting used to it, it's easy to make some simple mistakes, easy to get a little bit confused. So again, the workflow, once we have our problem, we need to decide how are we labeling our edges. We need to decide which edge is the hypotenuse. That's the easiest one because it's always, always, always opposite that right angle. Once we have the hypotenuse, the other two edges, it all depends which angle we're working with in the problem. In this case, we were working with this angle. That means the edge opposite that angle is the opposite edge, and the edge that's touching that angle or next to is the adjacent edge. Once we've labelled those edges, we look to see what do we know and which trigonometric ratio relates to those edges. We've seen how we can remember our trigonometric ratios. If I was to find the whiteboard, I'm actually going to just write them again because it would be quicker to write them than it will be for me to get that old whiteboard up. So sine is equal to the opposite over the hypotenuse, cos is equal to the adjacent over the hypotenuse, and tan is equal to the opposite over the adjacent. We've seen how to remember these. We either remember SOHCAHTOA, so SOHCAHTOA, or we assign this as a mnemonic, as sex on hard concrete always hurts those outer areas. So sex on hard concrete always hurts those outer areas. We can use those to remember our ratios. So going back to our problem, we've labelled our edges, we know the pieces of information that we're dealing with, we remember our ratios, and from those ratios we remember, or we work out rather, which ratio relates the information that we're dealing with. In this case, we had the adjacent and the opposite. There's only one ratio that relates the adjacent and the opposite. That is the tangent trigonometric ratio. Once we have that, we can then rearrange it to find the piece of information we're trying to find. In this case, we were trying to find the opposite edge. In other cases, we were trying to find different edges. We can rearrange those ratios so that we have the edge we're trying to find in terms of the other edge and some trigonometric function of the angle. We use a calculator to work out that value, or if we were programming this, we could use the functions that are built into the maths libraries of programming languages. Find our value, and that has then solved the problem. So once you get the hang of it, there's nothing to it, but just make sure you work through each of those stages correctly. Take your time with each one. Make sure you're getting each one correct. Make sure you understand fully what's going on at each stage. If you don't, if any of this overview didn't make sense to you, then please go back earlier into the video and watch back through, because each of these stages were described in detail as we worked through them. How do we determine the names of the edges in our triangle? How do we relate that to our trigonometric functions? And then how do we rearrange those functions and use them to solve for values? So that's how we use our trigonometric ratios to find a missing edge. In the next video, we're going to continue our look at these ratios to see how we can find missing angles. If we know the length of two edges, we can use the ratios to find a missing angle. So that's coming up in the next video. So this is going to conclude this video. I want to thank you guys a lot for watching. I really hope all of this made sense, and I hope that you enjoyed this video. Thanks a lot, guys.